section 6.4 is continuing this idea of a quadrilateral, of course, but we're going to go more specific with the type of quadrilateral we've already learned, which is a parallelogram. Okay, so notice the title is we're dealing with rhombuses, which you should know what that is, a rectangle, okay, of course, and squares, okay? Notice right below it says properties of special parallelograms. So the fact that they say that basically gives it away that these are all what?
Special parallelograms.
Which basically, I want to stress this. The fact that the last two sections, we've been focusing on what do we know about a parallelogram, and what do we know how to prove a parallelogram. So all of those properties that we already know about a parallelogram hold true for these three things as well.
Okay, because they are still parallelograms.
Exactly. So just keep that in mind. So you sometimes want to go a little bit more specific, okay? So a parallelogram, obviously, opposite sides are parallel, opposite sides are congruent, opposite angles are congruent, all of those things.
Okay.
In a rhombus, we can go more specific. Notice it says, by definition, these are all the definitions, it is a parallelogram, which we know what that is, with 4 congruent sides. So it has all of the characteristics of a parallelogram, and then some. Okay?
So instead of just opposite sides being congruent, all sides are congruent.
So if you can kind of give a visual of that, all right, a rhombus, it basically is going to have all those characteristics of parallelogram, but all the sides are going to be congruent.
Okay.
Okay. Rectangle, which you should already know this idea.
Hopefully rectangles and squares.
Yep. Parallelogram with 4 right angles. So it has all of those characteristics of a parallelogram, but this time all of the angles are right angles.
Okay.
Okay. So it's still going to have the opposite sides are congruent, which we are already familiar with rectangles.
Right.
Okay. Square is a parallelogram again with 4 congruent sides and 4 right angles.
Okay. So it gets more specific. It sounds like it's a rhombus and a rectangle both.
Yeah. If you notice, and I like that you said that, it's kind of a combo of the two prior. And I like that you said get more specific. So parallelogram's kind of more broad, okay? Then you're going to go more specific, okay? What things do we know about that parallelogram? Now, are all parallelograms going to be a rhombus, rectangle, or square? No. Okay? It doesn't have to have these characteristics. It's just if they do, we call it something else.
Okay.
Okay? So keep that in the back of your mind.
All right. We have up here a Venn diagram. And I know you guys have seen Venn diagrams before. And the parallelograms is just going to be our catch-all term for all of the shapes that we're looking at today. But more specifically now, we've learned 3 different types of parallelograms, 3 special types.
Okay.
And what were those 3 special types?
Okay, rhombus, rectangle, and square.
Right. And notice that we have an overlapping section. We have 2 circles, so there's 2 kind of larger ideas and 1 section that's overlapping in a Venn diagram. So of those shapes, what do you think is going to go where?
Okay, so like you said, the whole broad thing is parallelogram. So a Venn diagram kind of shows like that connection between some of the things.
Right.
So everything in that region is parallelograms. Within the circles are more specific, right? Is that what we're thinking? Okay. So I'm thinking probably what you're saying is start kind of maybe not as specific, right? Kind of break it down. So maybe a rhombus would be in one of the circle areas that doesn't intersect.
Right, because we said that a rhombus
is a parallelogram with 4 congruent sides.
Okay.
And then a rectangle is the other one that's not as specific. It's obviously more than a parallelogram. So it's a parallelogram with 4 right angles.
Okay.
And then the square was the one that kind of connected the two. It was the combo of the two.
Right. We said it was kind of it met all the criteria of the rhombus and all the criteria of the rectangle. So the square will be what's in the middle because that's both a rhombus and a rectangle at the same time.
So
it has the right angles and the congruent sides.
Gotcha.
Okay. Now, using that idea, and I'm going to do a little split screen action.
Yes.
So we can see this. We're going to keep up our Venn diagram. But I wanted to be able to look at some of these always, sometimes, never questions. And I know sometimes we struggle with the always, sometimes, never questions because they take some thought. They really do take some thought. And the first question said, we're just determining if these are always, sometimes, or never true.
Okay.
First one says, a rectangle is a square. So we're looking at a rectangle is a square.
Okay, so
Is that always?
when I look at that Venn diagram, and this, I like that you split that screen, because if you look at where the rectangles are located, it's in that whole circle there. And there is a region where there are squares that are rectangles, and then there's a region where there are rectangles that are not considered squares.
Right.
So I would say it's a sometimes. It's not going to always happen, because rectangles don't have to have all congruent sides, but they could, and when they do, it's obviously a square.
Exactly.
And the reason why, guys, and this is where some of you will say never, because you're thinking, okay, just strictly.
Is a rhombus. Is a square always a rhombus, sometimes, or never a rhombus?
Okay, going back again to that Venn diagram, and I see where the square is. It's in that region where it overlaps the rhombus and the square, or the rectangle, sorry. So basically, squares have characteristics of rhombuses, and they have characteristics of rectangles. And it always is going to be that case, because it's always going to have 4 congruent sides. Like,
Right.
There's no way that a square can be anything but.
So a square is always a rhombus,
Yes.
and it's always a rectangle. So it's always both, but it is definitely always a rhombus.
Yes, and it's because they're always going to have 4 congruent sides. You can't think of a counter example.
Right.
Right? If I think of a square, right, it's going to have 4 congruent sides.
Okay. What about this one? A rhombus is a rectangle. This is one that I have a lot of students miss.
Oh, I was going to say the same thing. Okay, so the initial thought sometimes is students will say no. Never going to happen. But this actually is a sometimes. And the reason why it's a sometimes is because of the fact that rhombus and rectangles have one thing in common. They're all parallelograms, okay? And where they connect in that Venn diagram, notice how they overlap, is in where the square region is, right? So rhombuses could be rectangles if it's a square.
Okay.
Or vice versa.
Right.
A rectangle could be a rhombus if it's a square. So it's a sometimes because it could be a square. A rhombus could be a square.
Yeah, and guys, if you look at the overlapping part in the Venn diagram, that kind of gives it away too. But yeah, there is sometimes that happens. But you're right, it only happens when it is a square. Okay, the next one. A rhombus is a square.
That's kind of like that first one we did, that choice A, or the first choice, rectangle is a square. A rhombus could sometimes be a square when it has 4 right angles, but it doesn't have to.
Exactly.
So this is a sometimes.
Okay, next one. A rectangle is a rhombus.
A rectangle is a rhombus. That's kind of like the rhombus is a rectangle idea. So that's a sometimes as well.
Exactly. And what about this next one? A square is a rectangle.
That's an always.
Uh-huh.
Because it's always going to have 4 right angles.
Oh, goodness. Kind of skipping on me. All right, and then this last one. A rectangle is a parallelogram.
That's always.
Always.
By definition, it's a parallelogram.
All of these are parallelograms, right?
And that's one thing, and I like that you ended that way. Everything in this, what they all have in common is that the fact they're all parallelograms. So they have to have something in common.
Exactly. Go back to our normal view now. Okay.
So, speaking of these special types of parallelograms, notice this slide, and I think initially when you read these corollaries, so if you're going to take a look at them, when I first read them, it kind of almost sounds like the definitions, right? So the rhombus corollary says it's a quadrilateral, or a quadrilateral is a rhombus if and only if it has 4 congruent sides. Rectangle corollary, a quadrilateral is a rectangle if and only if it has 4 right angles, so on and so forth. They're all biconditional statements, and technically definitions are biconditionals. However, the only thing about this makes this different than the definitions, if you go back to that definition slide, all right, notice the definition all says something about how the fact that they're parallelograms. So this slide, it just says, you have a quadrilateral, 4 congruent sides basically means rhombus. So you don't have to know, basically, based on these corollaries. Corollaries, remember, are a little more specific to a rule that we already know. So this is more specific to the definitions. So you don't need to know, okay, I have a parallelogram first, and then prove it's a rhombus. If you know you already have a quadrilateral and it has 4 congruent sides, it automatically means it's a rhombus.
Okay, great. So
Okay.
we don't have to know parallelograms.
Yes,
automatically.
and this is good, guys. The reason why I stress this is because when you start doing proofs, you don't have to prove it's a parallelogram first. So that's kind of nice. Notice the square corollary says quadrilateral is a square if and only if it's a rhombus and a rectangle. So again, that combo idea. Okay.
All right. First example, it says we're going to find the side lengths of this rhombus. Ooh, that's nice. They tell us it's a rhombus. What does that tell me?
Well, it's a parallelogram with four congruent sides.
Okay.
And I'm noticing the fact that 2 of the sides are labeled, so we're probably dealing with the side idea.
Exactly. And yeah, because there's lots of things we know about parallelograms that are also true about this, but the fact that all the sides are congruent. I have 2 sides that are adjacent that in a parallelogram would not be congruent, but because this is a very special type of parallelogram, it's a rhombus, these are also congruent. Okay, so what can I
We can
do
just
with
set them equal to each other. So 2y plus 3 is equal to 5y minus 6. So I get 3y equals 9. And so y equals 3.
Great. Now, is that all they asked me to do is find y?
No, it says find the side lengths of the rhombus. So I'm going to substitute that back in.
Wonderful.
So let's find ME first. So
Okay.
we'll do 2 times 3 plus 3. So that is, 6 plus 3 is 9. So that's that side length. And technically, all of the sides are 9 because it's a rhombus. So if you put it back in for EK just to double check, so 5 times 3 minus 6, that's also 9.
Right.
So all of the sides.
And do we need to list all the sides as 9?
No, you could probably just say all sides are 9 or just 9.
Yeah. Because we know that all sides are congruent. Mm-hmm. So sides are 9. Perfect.
All right, let's see. Yep. Before we get to some more examples, here's the deal, guys. The definition of rhombuses, rectangles, and squares are the minimum of what you're going to need to know, okay? And I think that makes this section a little bit more challenging because we already know going into what we know about those 3 parallelograms, but we limit ourselves. We have some theorems that are more specific, and these theorems are a must need to know, okay? So you need to understand these, so don't limit yourself, okay, just the definition. So this first theorem, none of them have names, which is no big deal, right? It says a parallelogram is a rhombus if and only if its diagonals are perpendicular. Now, notice this isn't a biconditional, and what does that basically mean?
So that means it works both ways. So if we already know the diagonals were perpendicular, we also then know it's rhombus.
And then vice versa, if it's a parallelogram that's a rhombus, then the diagonals are perpendicular.
Right. So it works both ways.
Now, the key here is that it does say something about a parallelogram, and I'm going to stress that because we're going to learn another type of quadrilateral that also has diagonals that are perpendicular. That's not a parallelogram. That's not going to be a rhombus. So this idea of knowing it's a parallelogram is important first. Mm-hmm. Okay, so unlike the corollaries that we learned where it was just a quadrilateral, knowing these are parallelograms is important too. Okay?
Yeah. And guys, we know things about the diagonals of a parallelogram. Mm-hmm. We know that they bisect each other.
Yes.
But this is something else that we know about the diagonals. So just something to be aware of, because just knowing diagonals bisect each other just means it's a parallelogram in general.
Yes.
Diagonals being perpendicular means that this is
this theorem is going to be good to help you prove if it's a more specific parallelogram. Okay? Now notice it says works for squares also. Why?
Because we know that squares are rhombuses.
Exactly. So if you look at this picture, what would you be able to conclude if I did tell you this was a rhombus?
Then I would know that segment DC and AB were perpendicular.
So that's essentially what that's saying. So these would be perpendicular, knowing that all rhombuses have diagonals that are perpendicular. So just keep that in mind. That's a very useful tool when we get to proving some other types of parallelograms.
Okay, so this next one says, again, we have a parallelogram is a rhombus if and only if the diagonals bisect a pair of opposite angles. Okay, so we're talking about a parallelogram being a rhombus. That's, again, talking about this idea of a rhombus. If and only if, another biconditional, each diagonal, so we're looking at each one individually, bisects the pair of opposite angles. Okay, let's talk about this one because that's kind of wordy.
Yeah, this one is can be kind of tricky. And I think, to me, of the years I've taught this is probably the one that most students will forget about.
Yes.
It's not going to be as useful when you do like a proof all the time, but it's something that, again, we need to understand.
Right. This one's saying that if I look at just each diagonal individually, so starting with just DC, this diagonal is going to bisect a pair of opposite angles.
So that means angle ADB and angle ACB. Those are the pairs of opposite angles.
Yes, these whole big things. Sorry.
Yeah.
Yes. And if those angles are being bisected, that would mean that ADC
C is going to be congruent to angle CB or CDB.
Right.
And then the other pairs are going to be congruent. While she's writing that, I'm going to kind of share with what I was thinking too. The fact that you're talking about opposite angles, well, the fact that we already know this is a parallelogram, aren't opposite angles congruent?
Opposite angles are congruent.
Okay, so you're basically bisecting a pair of opposite angles that are already congruent. So wouldn't each of those pairs that make up those opposite angles are going to be all congruent, right?
Absolutely. So really, these two are congruent, but it's also congruent to angle
ACD and angle DCB.
So all four of these are congruent angles. Absolutely.
And you could do that with the other pairs of angles with the diagonal. So those pairs will be congruent and those pairs. Now, they're not all, I like that you put them with 2 tick marks because they're not all congruent. Because in a rhombus, this is again talking about a rhombus, not all the angles are congruent. Now, what if this was a square?
Then all of those parts would be congruent.
And what do you think that all those angles will be then?
Well, if each diagonal or each angle is 90,
And
I
you
bet they'd each
bisected-
be 45.
Now, that's only with a square.
Right.
With a rhombus, that's not the case.
Okay.
All right. I think we have one more theorem, I believe. And this one, notice the last two we're dealing with rhombuses. This one is talking about dealing with a rectangle. But again, notice it says works for squares also. Why is that?
Because squares are rectangles.
Exactly. So again, it starts the same way. A parallelogram says dealing with a rectangle this time. If and only if. So it works both ways. Its diagonals are congruent. Okay, so lots of stuff that we're dealing with diagonals. Okay, so in this picture, if I told you this was a rectangle, this figure, then what would we be able to conclude?
We'd be able to conclude that DA is congruent to FB.
So these two segments would be congruent. All right, now this is true when it's a rectangle, which means it works for a square as well. Okay, so this theorem proves when a quadrilateral is a rectangle. Now, it doesn't necessarily prove it's going to be a square. You might need to do something else to prove it's a square as well. Right? Now, would this work for a rhombus?
Sure. No, it wouldn't. It would only work for a rectangle because rectangles, the only time it'd work for a rhombus is if it was a square.
Exactly. So, and even if you look back at this picture with the rhombus, these diagonals here don't even resemble being congruent. Okay?
Right.
So, not saying you base it off what it looks like, but sometimes it's easy to kind of see that that's going to be the case. All right. So again, another good theorem to make sense of. All right. So let's apply this. Sorry.
Sounds good. All right. So we've got a picture. And they tell me that this is a rhombus. That's nice that we know what it is.
Yes.
Because then we know a lot of things about this figure.
We know a ton of stuff.
And I'm going to go ahead and mark what they've given me. They've told me that the measure of angle BCD, this whole angle here, is going to be 103. And they tell us that AE is 6. Oh, goodness. Okay, 6. And DE is 8. And then they ask us to find some things. The first thing they ask us to find is the measure of angle DBC. DB, where'd it go? C. So this angle right here. Okay.
Okay.
Now, let's think about some properties. 'Cause since we're talking about an angle, we have one other angle measure. What do we know about angles?
Okay,
within a
well,
rhombus?
I'm going to just kind of break it down to begin with. Okay, we know rhombus is a parallelogram, so I know opposite angles are congruent. I know consecutive angles are supplementary.
Okay.
I also know that in a rhombus that the diagonals bisect opposite angles. So
Right.
here's what I'm thinking. The angle that they give you, DCB, is kind of in a sense consecutive with the angle we're trying to, but not completely. It's consecutive with the angle ABC. So if I can find angle ABC, that's going to help us find angle DBC.
Perfect.
So I'm going to take 180 minus 103, and that gets me 77. Now, that's the measure of angle ABC.
Right.
Okay? And we learn, because it's a rhombus, that those diagonals bisect each other. So segment DB bisects that angle, so I'm just going to divide that by 2.
The segments bisect each other, but they also bisect the opposite angles.
Yeah, that's what I was kind of leaning towards. It bisects that angle, which basically means I'm going to take 77 and cut it in half, and I get 38.5 degrees for that angle there.
Okay. So the measure of angle DBC is 38.5. Love it. Okay, now, moving on to a segment. We're trying to find the measure of segment BC. So that's talking about this segment right here.
Okay. Okay, so here's what I'm thinking. The fact that they gave us AE and DE, those measures, probably means something to this problem.
Probably.
And I noticed that those two don't involve the actual sides directly. Those are parts of the diagonal. So I have to think about, in a rhombus, what do I know about the diagonals? Because that's what they're labeling. And guys, that's the thing. It's like they're giving you it for a reason. So think about why. So what do I know about a rhombus? Well, I know a couple things. The fact that it is a parallelogram means the diagonals bisect each other. So that means AE and EC are going to be congruent.
So that's also 6.
And then DE and EB are congruent. So that is also EB is 8.
Okay.
Okay. The other thing, this is the big one. The fact that it's a rhombus, diagonals are perpendicular. So this diagonal DB is perpendicular AC. And notice when you label that stuff, hopefully you're seeing a right triangle.
Yeah.
And the fact that we don't know BC, which is the side we're trying to find, and it's a right triangle with 2 sides given, I could find the third side using the Pythagorean theorem.
Perfect. So let's do that.
Okay, so 8 squared plus 6 squared, or 6 squared plus 8. It doesn't matter. Does not matter. Equals BC squared. And so that's 64 plus 36. And when I add those, it's 100. And when I take the square root, BC is 10.
Wonderful. So notice how the problem that we were looking at, there's lots of different things we can determine based off of knowing all those different properties. And be really careful, because a lot of us are probably comfortable with the basic parallelogram properties. It's getting these more specific figures. These are going to be a little bit more thought-provoking for you because of that.
Yeah. It's a step beyond that what you're used to. Like this one involved mainly concepts about the diagonals. Not a lot about the fact that, okay, well, yeah, all 4 sides are congruent. That had nothing to do with it.
Right.
So you need to kind of think beyond. All right, we have one more example, and this should kind of look familiar. We did something like this yesterday. What we did with the coordinate plane types problems, we proved when something was a parallelogram. Now, let's read the problem. It says, given that PQRS is a parallelogram. So you already know it's a parallelogram. So do I need to prove that it's a parallelogram?
No.
No. It says, decide whether it is a rectangle, rhombus, square, or none of them. So it may not be any of those specific types. It says, justify your answer with work and an explanation.
Whew, okay.
Now, I put a coordinate plane here, but we talked about this the other day. We don't really have to have a coordinate plane. Something I might even do, I'm just going to show you what you could do. Instead of graphing it, because graphing it's not going to, I'm trying to trash it.
That's okay.
Yeah.
Just throw it down there.
Okay. Sorry about that, guys. Okay. So what you could do, instead of graphing it, because I don't want you to rely on the graph, nor does Miss Hogrady. All right?
Right.
So what you could do, notice the name, it kind of gives it an order. So you could just draw kind of a parallelogram, and you don't really know what kind it is, and just label PQRS. Now, it's very important you do it in consecutive order. If you need to graph it to kind of see that, you can do that as well. Graphing just takes a little bit more time, and that's not showing what it is. Okay?
It's not showing anything.
No, it's not. It's just you're drawing it. Okay?
It's giving you a visual, but that's its only purpose.
Okay, so here's what we got to do. We got to think about how we're going to go about proving it's one of these three things or none of them.
Okay. Well, I'm thinking about some of the properties that we've learned.
Okay?
We've learned that if the diagonals are congruent, it'd be a rectangle. We talked about if the
Or square.
Or a square, yeah. We talked about if the diagonals were perpendicular, that it would be a rhombus or a square.
Okay.
And so really by looking at those diagonals, that's what made it more specific. Because all those properties we really looked at dealt with the diagonals. We talked about the angles too, but the opposite angles being bisected, I think that's probably not going to be helpful with a coordinate plane.
No. And I like that you're talking, because with diagonals, you can find if they're congruent or not by using distance formula. You can find if they're perpendicular or not by using the slope formula. Yes, you could deal with finding the side lengths. You could kind of narrow it down that way. That's just a lot of side lengths you got to find. Okay.
Right, and then that still doesn't tell you if they were all the same. That could be a square or a rectangle.
Yeah, because bottom line, a parallelogram, we already know it's a parallelogram. So we already know opposite sides are congruent. We know opposite sides are parallel. We know those things, so we don't want to do more work than we need to. So I like that Ms. Hograve said, let's kind of be more specific. The diagonals approach, to me, is the most specific way. Okay, so diagonals in this picture, what are the two diagonals?
Let's see, PR and QS.
Okay, so let's decide first, okay, because really it's narrowing down. Is it a rectangle or rhombus approach? Okay, because if it's a rectangle,
then the diagonals would be congruent. So we want to look at their side lengths, the measures.
Okay, so let's find the lengths of PR and QS. So we're going to use the distance formula to do that. So PR's length, so we're going to use that distance formula.
Okay, so I'm going to take 3, and I'm going to do plus 2, quantity squared, plus our 1 plus 3, quantity squared. I'm just doing the pluses because it was minus negatives.
Yep.
And that's going to give me, let's see, a 5 squared would be a 25, and then a 4 squared would be a 16. So radical 41.
Now, that's as far as you need to go. You don't need to put that in your calculator, give a rounded answer, because all we're determining is if those measures are the same.
Okay.
So that's one diagonal. Okay, let's find the diagonal QS.
Sounds great. Okay, so now I'm going to take 3 plus 2, quantity squared, and negative 3 minus 1, quantity squared. And that's going to give us a 5 squared, 25, and a negative 4 squared is 16. Oh, we still get a radical 41. Okay, so we already know this definitely is going to be a rectangle of some sorts.
Okay, so I'm going to make a little note here. Diagonals are congruent, which basically means it's either a rectangle or it could be a square, right?
Right, because a square is still a rectangle.
Yeah. It's just, we can't say it's a rhombus because rhombus doesn't have that property. We're not going to say none of these because in a parallelogram, diagonals don't have to be congruent.
Right.
Okay, so now we can eliminate these choices right here.
Okay. So now let's take a look and see if the diagonals are perpendicular, because that's true of rhombuses.
Okay.
All right, so starting with PR, if I'm trying to find the slope, I'm going to take, let's go negative 3 minus 1 over negative 2 minus 3. So a negative 4 over negative 5, so 4/5. And then let's take a look at QS. So for QS, I want to take maybe 1 plus 3 over negative 2 minus 3. That's going to give me 4 over a negative 5. Now that's negative 4/5. That's not the same.
Okay, these are obviously different.
Yeah, we weren't looking for parallels though. We were looking for perpendicular. So we want them to be opposite reciprocal slopes. And those are opposites but not reciprocals.
Okay. So these basically aren't perpendicular.
They're not perpendicular. So in order to be perpendicular, one would have to be 4/5, the other would have to be negative 5/4. Okay. So don't forget about the reciprocal.
Yeah, maybe make a little note here. So perpendicular means the opposite reciprocal. All right. Make a little note, side note. So like she said, the QS's slope should have been negative 5/4 if you end up being perpendicular. So the diagonals aren't perpendicular. So will that narrow down what my answer is then?
Yeah, because then we know it's not a rhombus. Therefore, it cannot be a square either, because a square is also a type of a rhombus. So this one is just a rectangle.
Now, it says justify your answer with work and explanation. Now, I don't have a lot of room for an explanation, but actually I could probably scroll down a little bit. So if I was explaining this, why is it a rectangle? Why would we say it's a rectangle?
It's a rectangle because the diagonals are congruent, but not perpendicular.
Okay. Now, again, you could go about this different approaches. I see this every year. I'll see students that will want to find the lengths of all four sides. Okay?
Or even just two consecutive sides.
Or two
because
consecutive.
They know, yeah.
Because you already know it's a parallelogram, so you know already. Here's the deal. You already know opposite sides are congruent. Bottom line.
Right.
Okay? So you could find out the consecutive sides, and what she means by consecutive are the ones kind of right next to each other, the adjacent sides in a sense. So if you could find out these sides, like PQ and QR, you could find out how long those are, and that would narrow it down. Well, is it a rhombus or a square idea? Because maybe the sides are congruent. If not, then it's a rectangle. You would still then have to find out if we have right angles or not. So you could find the consecutive sides and their slopes to see if we have a right angle.
And if one is a right angle,
then they're
all
gonna
of them are going to
because
be
it's
right
already
angles.
a parallelogram.
So we already know opposite sides would be, and those consecutive angles would also be supplementary.
Bottom line, guys, is notice how many things we had to do. We
Still
had to
need
do
four.
4 different things. Okay, so you need to still find 4 different things. And notice we use the slope and distance formula on this.
And you will, regardless of which approach you use.
Exactly.